The amazing things our next speaker has done in the laboratory was recognized by the 2012 Nobel Prize in Physics. And today we're going to hear not only about the amazing things done in the laboratory, but by the miraculous things done in the laboratory of resurrecting Schrodinger's cat. David.
I'll set the timer. Yeah, when the yellow light goes on, that means what?
When the timer goes down to 0, it's 30 minutes, and then we go for questions.
Okay. All right. Yeah. Let's see. And the pointer. Oh, here it is. No, I got it. Okay. Yep. There's one here. Thank you. Thanks, Rocky, and thanks for the invitation to come here. So I know I'm here primarily because of the prize this last year, and so what I want to do is rather than teach, the abstract said a little bit about quantum information processing, but this is more going to be the story of what's led up to this in the last few years, and in particular in the atomic physics domain. I have to say at the outset, I shared the prize with Serge Haroche from Paris, and I think we both feel, of course, very flattered, as you can imagine. But I think it's certainly, our having been chosen is more reflection of a very large community of people. And I will tell you more about my story and involvement in this, but it really does involve a huge number of people around the world. So to start with, I think I don't have to explain Schrodinger's cat, but I think the reason it's interesting to think about is that the founding fathers, including Schrödinger, would sit around discussing the implications of quantum mechanics, and they tended to think about simple systems. But what bothered Schrödinger was the idea that, well, in principle, anyway, quantum mechanics, the theory should scale up to large systems. That is this continuous evolution that we know about in superpositions and so on. And so I'm not going to discuss the example, I think you know, but basically what he said to sort of express his concern, that quantum mechanics should work at the macroscopic level was his cat, where at the half-life of the particle, you'd get this entangled superposition, the correlation between the decayed particle or the radioactive particle and this cat. So it'd be an equal superposition of the particle undecayed, the cat alive, and the particle decayed and the cat dead. Not either or, but both at the same time. And of course, we know that when we measure the system, it collapses into one of those states or the other. Schrödinger continued to be bothered by this, that is, extrapolating quantum mechanics to the macroscopic world. And he said, well, in the early 50s, he said, well, maybe, one way out of this was, well, maybe we're kidding ourselves by thinking of these experiments in terms of a very simple system, and then we get into trouble when we extrapolate to the macroscopic world. So you can read the quote there. He said, basically, we can't play with these small systems where we're having these Gedanken experiment discussions. But of course, we know we can. And these days, we can play these, at least kind of do the Gedanken experiments that the founding fathers were talking about. And it's not very hard to say. What we need is we need good control of the systems and isolation from external perturbations. And so the kind of the story I'm going to make is how we get down to individual or small numbers of quantum systems how we can control their internal states, and in our case, the case of atoms and ions, how we can control their motion down at the quantum level. And basically, this has led up to this subject of quantum information. And as I said, this is more my story, but I think it's gives a good example of what's been going on with the work of a lot of other people. So my story starts as a graduate student in Norman Ramsey's lab at Harvard. This is Norman. This is me getting close to the boss there. At that time, Norman and his close colleague Dan Kleppner had just invented and demonstrated the hydrogen maser. Norman wanted to have accurate measurements of all the hyperfine frequency of all the hydrogen isotopes. So my project was to measure the deuterium hyperfine frequency with a maser. And I like to say I think I'm the only one in the universe that has this number memorized there. That since it was the main result of my thesis. Nevertheless, I mean, even at that, I was sort of hooked on precision measurements by that time. But and even at that time, we were, of course, one of the ingredients to get these relatively high precisions is we need to control the environment. And even in the maser systems, we're working with these superposition states that are lasting about a second. And although in this case it was, of course, on a large ensemble of atoms. So from there I went to Hans Dehmelt's lab as a postdoc, and actually John Harris was reminding me this morning, he was a student when I was a postdoc there. And anyway, so I went there. Hans had also done some nice spectroscopy of atomic ions, which is what first attracted me. But he wanted to push on his experiment to measure the magnetic moment of the electron, which I think can be calculated very precisely. And the idea was to do precision measurements on it. So in these what we call a trap, it's some electrode structure. What we can do is we can excite the electrons, a group of electrons, and we can put it in a simple circuit to detect we drive at the resonance frequency of the electrons in the trap. And it turns out we can set up a simple circuit like this where the signal out is proportional to the number. Well, at that time, it became pretty clear that to get the highest precisions in any measurements, we wanted to get down to single electrons. And so in this experiment, basically, all that we did was we drove the amplitude of the electron motion so that occasionally one of the electrons would strike one of the electrodes and be lost, and you'd see a staircase. In this case, we started with 7 electrons and saw this step as these steps as each of the electrons fell out of the trap. John, do you have that pointer? This one seems to be dying, but oh, okay. I guess it's yours. Okay, sorry. Thanks for that. Anyway, so this was one of the things we wanted to do. This was the start of getting down to individual particles that we could play with. And as I said, this was a precursor to the measurements that Hans and his colleagues later did. Oh, thanks a lot. Okay, thanks a lot. That Hans and his colleagues made a precise measurement on the magnetic moment, and later that led to Hans Dehmelt's, in part, the reason he would receive the prize later on. Anyway, at that time, I was still interested in spectroscopy, and Hans and I had some ideas about cooling the ions, and I'm not going to describe all the cooling methods. I think most of you know that if you shine a laser in on particularly a bound particle, if you shine it slightly below the resonance frequency, the ions will cool because they preferentially absorb the scatter photons and get the momentum kicks that slow them down when you're tuned to the low frequency. So anyway, we had some ideas along this line, and also Ted Hench and Archel, a famous laser physicists had an idea at the same time. They looked a little different at that time, but they're pretty much the same. Whoops. The reason for that was, or at least one reason to do the cooling was in spectroscopy, although it's a small effect, relativistic time dilation is a factor because the ions are jiggling around in the clock or in the trap where we're trying to probe their spectra. And although it's a very small effect, we're now down at precisions where we have to take care of the time dilation shift at a very fine level. Okay, another possibility. Okay, here we go. So anyway, one interesting coincidence, near coincidence, is I knew that Hans Dehmelt had gone to Peter Toshek's lab in Heidelberg at that time to work on this cooling idea. And when I got to National Bureau Standards at that time, which is now called NIST, we finally got some support to be able to try this experiment. So one interesting aspect of this, both the groups are working on. I didn't know where they were in their experiment. I only know that Hans had gone there to work on this problem, and they weren't really aware of our experiment. You notice that these first papers were published pretty close together. To be fair, if you look at the submission dates, though, I guess you'd have to say they won the race because their paper reached PRL a day ahead of time. In their experiments, what they looked at is both experiments, the evidence was pretty crude, but they could see a lengthening of the lifetime of the ions in the trap. It could be attributed to this cooling effect. In our experiment, taking a lesson from the electron experiments here, what we did is we just, rather than driving the electrons, we looked at the thermal currents that were induced in the electrodes, and the noise basically from these thermal currents gives a direct measurement of the temperature, and we could see the cooling effect in that way. So this was our group in 1979, and that was part of the original crew on these experiments. This was not too long ago, and I'm always embarrassed. Yeah, these guys, Wayne Otano and Jim Berquist, look pretty much the same, but these other guys didn't fare so well. Anyway, this is, of course, we've gotten a lot bigger now. I'm not going to go through all the names here, but we're supported by a lot of good young people working on these experiments. So after those first cooling experiments, just as with in the electron experiments, to get high accuracy, we'd like to go down to single ions. And in these first experiments here, Toshek and Dehmelt clearly beat us on these submissions. One interesting thing about their experiment is that it's a little hard to see. This describes this kind of trapping structure, and with single barium ions, it's one of the very few ions that has a fluorescing line in the visible. It's a blue line. And you can actually, in these experiments, you can, with this modest modification, magnification, you can actually see a single atom, a single barium ion with your eye. In our experiments, we chose to work on mercury. This was the main focus at that time. Still was to make atomic clocks, do high resolution spectroscopy. And I'll tell you why in a second here. In those experiments, we for this cooling transition, the challenge was that we needed to go to a fairly short wavelength, and this 194 nanometer laser that Jim Berquist developed was actually the most powerful, very weak laser, but the most powerful CW laser done in this regime for many years. Anyway, that allows due to the cooling, and the idea of so what was interesting about it, among other, well, here's a picture of the ion taken in a UV imaging camera. The interesting about mercury, one of the interesting things was it had a transition from the ground to excited state, and the lifetime was fairly long, meaning, of course, that absorbs over a very narrow range of frequencies, and therefore can provide a standard. And the 15-second lesson on how atomic clocks work, basically we want to find the condition where the atoms absorb maximally. When that occurs, then we know the frequency of the laser is tuned exactly to resonance, and to make a clock, we just count the cycles of the oscillation of the laser. So that was one of the motivation, and actually the one. This kind of experiments it's fairly simple to tell when the absorption is made. So the idea is that if we start the atom down here, we apply the radiation, and if the radiation is tuned off resonance, then when we turn on this cooling and detection laser, we see this fluorescence. On the other hand, if it's made the transition up to this D level in this case, and when we turn this laser on, the fluorescence is absent. And to give you an idea of the kind of data we see is that when the atom remains in the ground state after applying the clock laser, we see fluorescence, and conversely, when it's promoted up, then the fluorescence essentially goes away. And if we just put a discriminator halfway in between, we can tell with essentially 100% efficient when the atoms make the transition. Now, this doesn't mean there's no noise in the problem. We're limited by the quantum noise in whether or not the atom makes the transition. So, anyways, this actually is when I say a little bit about the quantum information stuff, this provides a nice way to detect the states of a qubit. We could make a qubit on this transition. So after that, it was, even though we were doing laser cooling, it'd be nice to get down to the ground state of motion of these ions in the trap. And so typically, for the typical conditions in the experiment, the laser cooling, the simple kind of laser cooling, so-called Doppler cooling, gets us down to temperatures of a few millikelvin, which typically occupies several of the quantum levels of the motion. You can think to a very high degree the motion of an ion in the trap is harmonic, so we have this equally spaced ladder of energy levels that are, of course, shared by both internal states. So the trick is, of course, the energy separations on this are about 9 orders of magnitude smaller than the typical optical energies. Anyway, the way we can do the cooling is actually, we first want to cool down to the ground state and then do manipulations through there. And it turns out the idea is pretty simple. Since this line is fairly narrow, when we probe this transition, what you can think of is classically, if you're sitting on the ion, it's going back and forth, and when you look at the laser, it looks like it's frequency modulated due to the first-order Doppler effect. And we see this FM spectrum. So on the quantum picture, what this center line represents is the case where we're driving the electronic transition, but preserving the motional state quantum number. And the upper sideband in this FM spectrum corresponds to the case where we're increasing the motional quantum number by 1. And similarly, for the so-called red sideband, it's a case where we're reducing the quantum number by 1. So the way to get cooling out of this is actually fairly simple. We need to keep one thing in mind, and that is that after exciting the ion to this excited state, when it decays, the conditions in the experiments are such that upon re-emission, to a very high degree, the photon is emitted, the recoil goes into the apparatus rather than the kicking the ion, very much like it is the Mossbauer effect, but in the optical regime. So the idea of the cooling then is really pretty simple. We tune our laser to this lower sideband. That's the one that induces these transitions where the the motional quantum number is reduced by 1 for each excitation. And when the atom decays, then in the overall process, we've reduced the motion quantum number by 1. And very simply, we just leave this laser on at this frequency, and the ion walks down this ladder of states. To tell that we're in the ground state is actually pretty simple, because in these experiments, when we try to drive this red sideband further, the fluorescence stops because there's no n equal -1 level to go to. So when we look at these at the red and the blue sideband here on an expanded scale, basically the red sideband starts to disappear, and it turns out it's very simple. These states, at least averaged, look like thermal states, and in fact the strength, there's a very simple expression that tells from the strengths of the sidebands we can get an idea of the mean occupation number. And anyway, just the fact that it's almost gone here indicates that we're very close to the ground state. And it's this, I'm going to come back to this in a minute, but it's basically, one thing to keep in mind is this, the fact that in this transition here, once we reach the ground state, this conditional dynamics, that is, whether the photon is absorbed dependent on these quantum states, is what gives us, it's one way we can make logic gates in these experiments. So just to come back to the clocks, it was actually Jim Berquist in our group that really took this on, and we started this in 81, and it was only in the last decade here that we really got very high accuracy. Anyway, just some of the features. There's many things we have to worry about in these experiments for the high accuracy. The nice thing is that just the trapping alone means that on average the velocity goes to 0, so we get rid of the first order Doppler effect. As I mentioned, laser cooling suppresses time dilation shifts. In this experiment, we wanted to go to 4 Kelvin. We do have to worry about black body shifts, the thermal radiation in the room. But the reason we actually did it, the shift in mercury, the black body shift at room temperature is fairly small. The reason we went to 4 Kelvin was that it turns out mercury in the excited state, and when it collides with a neutral mercury atom in the background, it makes a dimer and kills the clock ion. So, and in these experiments at the room temperature, we could only keep the ions around for on the order of 10 minutes, which was about how long we needed to get the lasers tuned up. So we went to 4 Kelvin simply to freeze out the neutral background gas composition of mercury, and we literally went from lifetimes of 10 minutes to 6 months in one case. So anyway, after a lot of hard work on it, controlling many other systematic effects, in 06, the mercury, it could get down the uncertainty, which we express fractionally because we can always shift the frequency. So our measure is the frequency uncertainty divided by the frequency. We got down to about 7 parts in 10 to the 17, and why we were happy with this was the first time that any clock had ever done better than the accuracy of the cesium beam clock, which works on hyperfine transitions in cesium. Of course, it was a moving target over all this time, but this was the first time, and in some sense we could say maybe it's clear now, I think, that the optical clocks will probably be better, but probably the cesium clock will remain the definition for a very long time. And I've only featured our experiments here. There's many interesting experiments going on around the world, and they're summarized in this paper here. So what about Schrodinger's cat? Just say, our version of this is the following. So we put the ions in the ground state, and we prepare, I'm changing labels on you here, but think of the S and the D states in mercury. So we put the ion in the ground state of motion and put it in the lower energy state. And then what we do is we create a superposition just by driving this transition coherently for a certain amount of time. And it turns out with lasers, we can make forces such that they act only, well, they can act on both, but differentially. In this simple example, we we're able to make a force on the, what we're calling the spin up, the excited state in this transition. And what we could do is arrange this dipole force so that it excited that part of the wave function. So you want to think about it oscillating back and forth at some instant at time. It might be on the left side of the bowl there. And then just to kind of summarize things, we flipped the spin and applied this same force but with a different phase relative to the first excitation. And at some instant of time then we could reach the situation where the atom is in a state where it's both on the left and the right side of the bowl correlated with the internal state. And we're saying this is like Schrodinger's cat. Obviously the microscopic property correlated with the atom or the radioactive particle decayed or not is the internal state of the atom. And although it's a bit of a stretch, we're saying the more macroscopic classical particle is this oscillation of the atom in this atomic bowl. Now it is very small. In these first experiments, we would separate the wave packets correlated with the internal states by about 10 times the wave packet size. And you might say, well, this is too small to call it a Schrödinger cat. I mean, you might believe you could make the analogy if we could separate them by a centimeter. If you say that this is too small, then you have to say, well, where's the dividing line? Where does things become classical macroscopic? And there's really no way to do that. So we would argue this, at least it has all the features of Schrodinger's cat. So anyway, a little bit about quantum information. What really got things, there were some ideas about, among others, Richard Feynman, who a particle physicist know well. But things really got going when computer theorist Peter Shor in the mid-90s showed that if you could make this thing we'll call a quantum computer, you could efficiently factorize large numbers. And the reason that's, of course, of consequences of basically all encryption is done with using algorithms where the security is derived from the inability to factorize large numbers. Anyway, in an atomic physics meeting in Boulder in '94, Arthur Eckert, who was well versed in this and other quantum ideas, came and explained this idea to us. And I think it's fair to say almost all of us in the audience weren't familiar with this idea. Anyway, two well-known theorists in atomic physics, Ignacio Serach and Peter Zoller, were there, and they came up very shortly with a scheme where you could, at least it was really the first scheme where you could make this quantum computer. And their idea was the following: suppose we have a group of ions in this electrode structure here, and you can think about this it's kind of like a pseudo-molecule. In this case, there's 3 n modes and the number of ions. It turns out all the modes, or in general, have different oscillation frequencies, so we can spectrally isolate them. And the idea in their proposal was the following: is that in general, that during a computation, all the ions will be in superposition states, and in general, an entangled superposition. And suppose you want to make a gate between this ion and this ion here. So their idea was what you do is you freeze out the motion, as we did for the single ion, and then you can consider the ground and first excited state as a qubit. So their idea was with a laser, you map the superposition state of the internal states of the ion onto this motional state superposition. And then if you can somehow make a gate between the motional state superposition and the internal state of this ion, then basically you've made a gate between these two selected ions with these focused laser beams. And so in this, I'll give you an idea how this works. So think back to the mercury ion that's in this conditional dynamics. What we can do is we can make a gate, a so-called controlled NOT gate, where we call this the control bit. The first bit's been mapped into this motional state superposition. And the idea then is we use this red sideband. So a simple logic table goes like this, where if the ion is in the n=1 state, then motional state, then when we drive this sideband, we can actually flip the spin. If it's in the ground state, there's no state for it to go to. And so we get this, basically that's the way we make these. Now it's a little more complicated than what I've shown here, but you kind of get the idea. And it turned out we were lucky. Chris Monroe, who was in our group from 92 to 2000, we kind of jumped on this, and we could do this first demonstration not very long after we actually got a preprint of their paper. So just, I'm not going to be able to really do justice to all the groups working on this, and these are some egocentric examples. Here I show D.D. Leibfried's pictures. He's in our group, and John Bollinger. And a lot of the groups around the world have been doing demonstrations of algorithms that kind of think of like subroutines in a quantum computer. One thing that's most interesting, and it goes back to Feynman and others, and the idea was to use these systems as simulators, that is, map one quantum problem of interest onto these other quantum systems that we can control. And so in our lab, it's a different kind of trapping structure, but we can hold ions in triangular lattices, and we can simulate, say, spin-spin interactions with the gate operations that I briefly described. The best work in terms of the least errors in these kind of experiments is done by Rainer Blott's group in Innsbruck, and Rainer's a strong competitor, but also has been a friend for many years. And there's many other groups, and just to give you an idea, these are the groups around the world just working on atomic ions in this business, so it's really a huge enterprise by now. Just to give you an idea what goes on in the experiments, what we dare to call a quantum computer is this little tiny thing over in a vacuum system on one corner of the room, and the experiments are dominated by these lasers. I showed this picture on the very first view graph. This is kind of an idealized structure we'd like to realize, and we started to scale down using lithographic techniques. And this shows a picture of one where we put all the electrodes in the surface, make a planar structure, and the ions are suspended above the surface. And the idea for scaling is to each one of these little tiny squares is a place where we can store one or a few ions to carry out these logic operations, and then we can build up the system by moving ions around in such an array. And this work goes on in several labs. Since I'm running out of time here, I won't go through some. I just want to say in these experiments here, we're getting in overlapping with a lot of condensed matter systems, and there are certainly viable qubits in that domain, and that people are discussing. Let me conclude by just one example. That we're coming back to the clocks. It turns out aluminum is very interesting, and we can use some of the simple ideas to detect. And although we could do it just like we do in mercury, it turns out that the transition we need is at such a short wavelength that we just can't find a laser there. So what we've done in this experiment is we've combined our clock ion with a logic ion, in this case magnesium. And this mapping technique that Sirac and Zoller first suggested for computing, what we do is we apply it twice. So after trying to drive this transition, in general, it's in a superposition state. We map onto a motional mode and then map that onto the magnesium ion, which we can detect efficiently with using state-dependent fluorescence. We have many things to worry about. I won't go through some of the interesting numbers since I've run out of time. Anyway, we're down at the level now where the uncertainty in the clock is a little less than a part in 10 to the 17. One thing one of the issues we have to take care of is the gravitational potential redshift, which is on the surface of the Earth, is at about this level. And let me just conclude with a little cheesy demonstration we did. So we have two clocks. This was one of the aluminum clocks on an optical table there. And what James Chow, our postdoc, did here is he first made a measurement comparing to the other clock, and then raised his clock by about 33 centimeters, and at least to the width in the airs, we got the answer we expected. Just to conclude, let me say, to me this is kind of disappointing, because after all this, all my career, the all we've done is made a yardstick with this thing. And the reason is that when we compare clocks now, we have to do it in the same location. And the reason for that is that simply that, especially here near the mountains, there's other ways to find the gravitational potential. But basically, for example, in Boulder, it's only known to expressed as a height about plus or minus 30 centimeters. So if we want to compare accurate clocks, they have to be in the same place. Of course, we'll take the high road and turn this around and hopefully be able to do geodesy with these things. So with that, I think I will conclude. Thank you.
Thank you, David. Truly remarkable. If there are questions, please use the microphones in the middle of the aisles.
And the question I have is this. One system where relation between a superposition state and two things that are separated happened very early in the history of quantum physics was the Stern-Gerlach experiment, where a spin up in the z direction of a neutral atom could be separated into spin up in the x direction and spin down in the x direction in different spatial locations. Has there ever been an effort to reunite those two and restore the superposition? And if not, is that a worthwhile thing to think about?
Well, I mean, it's a good question. In fact, the kind of experiment we do is really not much different than the Stern-Gerlach experiment. The one convenience in these, I showed the picture of the wave packets separated in this harmonic potential. One thing nice about the harmonic potential is these Gaussian wave packets, they don't spread as the wave function would in a two-slit experiment or the Stern-Gerlach experiment. But to answer your question, what we do to tell what's going on, and in fact to verify the coherence in the superposition, is after bringing them apart, we actually interfere the parts of the wave functions to show the interference fringes give us a measure that show the coherence between the wave packets. So.
It's hard to see from up here. Are there other questions? Okay, thank you, David, for a very beautiful presentation. Maybe we can